Welcome to solverfy.
Okay, so we're doing chapter 23, problem 33 here. So we have a thin circular ring of radius big R, and it has charge on it plus Q over 2 on the top half and negative Q over 2 on the bottom half, distributed uniformly on the ring. So there's a total charge of total charge of 0 on this, plus Q over 2 and minus Q over 2. Okay. So part A, what is the value of the electric potential at this point on the x-axis, a distance x away from the ring? Okay, so if you can see this element I have shaded black here on the top is just a small point of charge, positive dq, and the bottom, every point here is going to have negative dq, small amount of charge. And each of these points are diametrically opposed across the ring. And what that means is each of these, since potential only depends on the distance and not a vector quantity, these are both the same distance r along these blue dotted lines away from the point, and they have the opposite charge. So that means they're going to cancel each other out. And that's going to happen at every point along the ring. It's going to have an opposite point across the ring that cancels out its potential. So what that leads is to a zero potential across the whole ring at that point. Okay, cool. So let's go on to B now. So B wants us to say, what can we say about the electric field at the distance x along the x-axis? Let V equal 0 at R infinity. Okay, so if we look at these red vectors here we drew, we have DE bottom, which is along the line towards the bottom component of the ring, and E top pointing away from along the line towards the top component. And if you see, we can follow the example 21.9 in the book, but since the upper half and the bottom half of this ring are oppositely charged, that means the parallel components, meaning EX, are going to be opposite from each other, and they're going to cancel each other out. So what that means is, for the electric field, that EX, anything parallel to along this axis, is going to be 0. So that's good. And also by symmetry, we know that EZ is 0, so the only thing we have to find here is what EY is. So can we find EY? Well, we can. So let's start figuring out how to do that. So let's start by talking about just the Y component of the electric field for a small amount of charge. And this is given as DE, negative DE times sine of theta, where theta is these blue angles over here. That's how we just decompose this into EX and EY here. Awesome. So if we know DEY in terms of DE there, we can also write what the change in DE is, and that is negative 1 over 4 pi epsilon naught dq over r squared sine theta, and r squared by Pythagorean theorem is the same as r squared plus x squared. Look at this green triangle I add in here. This green triangle, we have x, r, and big R here. So let's rewrite this equation in terms of big R and x, and this is negative 1 over 4 pi epsilon naught dq sine theta all over x squared plus big R squared. Okay, so now that we have that, we can continue and rewrite what dq is and sine theta. So we should see that dq is given as q over 2, right? Because that's how much that's the total amount of charge in the top part. And we can divide this by the total amount of line we travel across this half circle, which is r times pi times dl. And this L is the component along the ring. It's not a linear one. It goes around from 0 all the way around to 2 pi r, or 1 diameter, all the way around the ring. So if we now have dq in terms of dl, let's figure out what sine theta. Can we write this as? Well, we can write this. This is pretty easily. This is just the opposite over the adjacent. So this is opposite over the hypotenuse, r. But we already figured out we could write r as x squared plus big R squared to the 1/2. So with all of these substitutions, let's go back here and we have dEy now equals -1 over 4 pi epsilon naught, and then we have q over 2r pi dl over x squared plus r squared times r over the square root of x squared plus r squared. Okay. So now if this is dEy, let's just integrate both sides and get just Ey. So we have Ey now is the integral from 0 to 2 pi r. This is all the way around the whole ring, dl. And this is times q, -q over 8 pi squared epsilon naught, 1 over x squared plus r squared, all to the 3/2, and we already wrote dl. Okay, cool. So this just comes out to just integrating L. So this just comes out to 2 pi r on top, and we see this is -q over 4 pi epsilon naught r over x squared plus r squared to the 3/2. And this is Ey. So now we can figure out, we know that all the other components are 0, so E vector is now written as -q over 4 pi epsilon naught r over x squared plus r squared to the 3/2 j. Cool. And we should also note that we could simplify this in some corner cases, and one of those that usually we might see is that x is much, much greater than the radius of the ring. And when this happens, our E simplifies to being -q over 4 pi epsilon naught x cubed r j hat, which if you might recognize as the electric field of a dipole, just a normal dipole separated by r. Cool. So now that we know this,